Now we're going to talk about confidence intervals. So we kind of already touched on the levels of confidence. Confidence intervals are directly related to that. Confidence intervals can be calculated for a lot of different things. So if we're looking at the confidence interval for a true population mean, the blank could be, right, where we want to know where the population mean exists. Sometimes it might be if we're looking at the relationship between variables. How related should these variables be in the population based on our sample? Or if we're looking at cause and effect and we're comparing two different sample means, maybe a control group versus an experimental group, what is the confidence interval of the difference between those two means, right? Or how different should those samples be in the context of a population? And so on and so forth for a lot of different other tests. But generally, confidence intervals can be calculated for a lot of different stuff, but it's always going to be related to how does our sample reflect an estimated region in our population. So let's do an example. These are going to be examples for confidence intervals for a true population mean compared to sample characteristics. So if we wanted to know where does a population mean exist based on a sample mean, a z-score, and a standard error of our mean, which we need our standard deviation and our sample size to calculate. Okay, using this formula, right, we can figure out what our confidence interval is. You notice there is a plus and a minus sign. That means you're doing two sets of equations. On one end, you'll have the sample mean minus the product of the z-score of interest, which is going to be associated with your level of confidence, and the standard error of the mean, which you calculate using your standard deviation and sample size. Okay, so the product of that subtracted from the sample mean is going to be the lower bound of your confidence interval. The product of these two things plus the sample mean is going to be the upper bound of your confidence interval. So we get two real numbers that exist in your unit of measurement that you've collected, and the true population mean should exist between those two values based on this information. So I've given you guys an example with a level of confidence of 95%. The z-score is going to be associated with your alpha regions. So again, in our class, we're going to use non-directional hypotheses, which means that alpha is going to get divided by 2. If you think about 95%, 100 minus 95 is 5%. 5% divided by 2 is 2.5%, or 0.025. That is the amount of error that we're willing to accept both above and below the mean. When you look this up in your z-score table, you want to look at the error or the probability that is as close to 0.025 as possible without going over it. Okay, because if we go over so let's say we had a choice between 0.0254 and 0.0251. Okay, 0.0254 is going to introduce a fractional amount of more error than we originally were willing to accept. So you always want to round down and not up. So if you looked up 0.025 or the value closest to 0.025 without going over 0.025 on the z-table, should be in the negative z-table, you should get a z-score that is 1.96. Now we say plus or minus 1.96 because we're both above and below the mean. So if you did 95 plus 2.5%, you should also get a z-score of 1.96. It'll just be positive instead of negative. Okay, so that's where z comes from. And then let's say we have a population of interest. In this particular example, I said my population is the age of individuals that live in mobile home parks. And I took a sample of 50 people. I had a sample mean of 60 years old with a standard deviation of 5 years. Okay, we're going to assume that our data are normally distributed, so that way it's nice and easy. That's the other reason why your sample should be normally distributed, is because when you calculate confidence intervals, it is based on using z-scores, and z-scores are under the assumption that you have normal distribution. So if you don't have normally distributed data, you kind of mess with your confidence interval calculation. But again, we're going to find the lower bound of our interval by taking our sample mean of 60 here. We subtract our product of 1.96 and our standard error of our mean. You can reverse backwards to the previous slide for the formula for standard error. Generally speaking, we're just going to use the value 1.96, okay, because the plus or minus is built into the equation. Okay, so if we're going below the mean, we have a minus 1.96. If we go above the mean, plus 1.96. But in terms of the z, just use 1.96 and then keep your signs straight here. If we put all of this into a calculation, right, and we calculated lower and upper bounds, we would end up with a confidence interval of 58.61 to 61.39. We use square brackets for confidence intervals because the square bracket means that we are including both of the values in our upper and lower limits. Okay. So if we were putting this into words, since this was a confidence interval for a true population mean, we could say we are 95% confident that the true population mean of the age of individuals that live in mobile home parks is between 58.61 and 61.39 years. I've given you guys a little bit more practice. Just for ease of reference, if you want to memorize these values, you can. If you want to paste this table somewhere where it's conveniently located so you can reference these values often, that's great. These are all common levels of confidence that are used in statistics or in our line of research. 90 through 99 are usually going to be the ones that we focus on. 95 is the most common. Okay. Over here, this shouldn't be P, this should be alpha. I'll make sure I change that on your PowerPoint. Okay. But alpha is going to, again, be 100% minus the level of confidence converted into a decimal point. Okay. And this is the total alpha between two regions of rejection, so a region both above and below the mean. These regions divided in half are associated with these z-scores, right? So z with 95 level of confidence with 0.025% or a 0.025 probability of error in both tails is associated with z-scores of 1.96, right? Same goes for a 99% confidence interval, which you could easily look up. A 0.005 probability of error on both sides of the mean would be related to a z-score of 2.58. Same thing goes for the 90 and the 68% level of confidence. These are some practice problems that you guys can work on. I've given you, what is this called? A spreadsheet that has a bunch of sample calculations in it. And there is a video that goes along with these sample calculations. So I would recommend watching that. Try doing the calculations first on your own if you can. I still would recommend watching the video though, because it does go through how your confidence interval width will change or where it will be located based on certain sample characteristics that are kind of a part of the formula. I've already mentioned this once, but I will just say it again. Your level of confidence and your alpha, which are conjoined together, are established before running the test. They are set a priori. Okay? They are based on how much error you're willing to accept, and it's up to the reader to determine if they accept your results. Okay? Let's say you have a significant difference with 10% of error, but you don't have a significant difference with 5% of error. Right? Is there truly a difference or not? There are other things that we can look into that will tell us if there is a difference or not and how large that difference is, but In terms of the reader, it's up to you to accept the level of confidence in the alpha level that was set by the researcher. Differences in reporting levels of confidence and probability of error. If we always wanted to be super, super precise, why not choose a 99% level of confidence with a p-value of 0.01 or a 1% chance of error? If you think about how our confidence interval works, 99% level of confidence is going to include a larger proportion of our distribution, right, with the regions of rejection kind of being on the end. So the larger we make our interval, the less precise it is, right? Because the further apart our lower and upper bounds are going to be from each other. So the less error we're willing to accept, the less precise our interval is, but also the harder it is to reject the null hypothesis or to prove that there is an intervention or an intervention or exposure effect based on whatever or how you're manipulating your subjects. So this is kind of the question that I just addressed, right? What happens if the confidence interval of our level of confidence increases, right? If our confidence interval, or if our level of confidence increases, so let's say we go from 95 to 99, our confidence interval increases, or the width of it increases, meaning less precise. Okay, so you can see that there's kind of a trade-off between how confident you want to be or how precise you want to be with your interval and how much error you're willing to accept. Because as your confidence interval increases, the amount of error you're willing to accept decreases, and as your confidence interval becomes more precise, or you try to be more precise or it narrows, the more error that you're kind of opening yourself up to. So larger confidence levels of confidence are associated with less precision. Narrower levels of confidence are associated with more precision. Again, it's up to you as the researcher as to what you're trying to accomplish. But it's good to know the side effects of everything, which is why 95 is kind of a nice sweet spot for most people. And that brings us to talk about the types of error that we can have. So, the way that we outline error is using this thing called an Orwellian sounding truth table. And it's kind of like one of those phenotype things where you're like, ooh, does someone have like a capital B and a little b and a big B and a big B, right? And then you have all of these different combinations of possible phenotypes that could be adopted by a person. The same is true if we're looking at, is the null hypothesis actually true or is it actually false? And do we accept the null or do we reject it? So we have all of these different possible combinations. Some of these are good choices, some of these are bad choices or types of error. So when we accept the null hypothesis, we did our statistical testing, we had a p-value greater than 0.05, we said we're going to accept the null. Let's say the null is actually true. If you accept the null when the null is true, you've made a good choice, right? If, however, we got a p-value less than 0.05, I'm just using 95% level of confidence with an alpha of 0.05 just for reference, okay? But if we had a p-value less than our alpha, that means we reject the null hypothesis, right? But what if the null hypothesis was actually true? This is going to describe our type 1 error. It is also known as a false positive. So you rejected the null. You said, "Yeah, we have a significant difference." When you make a type 1 error, that is a false positive. You have falsely accused somebody of being guilty, basically. In words, you reject the null when the null is actually true, or you're saying that there is a relationship or an effect based on your independent variable intervention on the dependent variable measurement, when in actuality there is no effect or no relationship. Another type of error can occur when we accept the null, so p greater than alpha is what we get in our statistical analysis, but in actuality the null hypothesis is false. Okay, so we should have rejected the null hypothesis. This is a false negative. In this case, we accept the null when the null is false. We say there is not a relationship or there is no effect when in truth there is an effect. So type 2 error we denote with beta. We haven't kind of commented on that yet. Type 1 error is alpha, which is the type of error that we've been talking about so far. But type 2 error is associated with power, which is the last cell of this table. And power is going to be when we reject the null and the null is false. So basically we are saying that there is a true effect of an intervention when in actuality there is, right? So all of any of our results that we got is purely due to the intervention, or there is a very, very, very small chance that error or other confounding variables have affected the results that have led us to this conclusion that the null hypothesis is wrong. But statistical power is going to be calculated by looking at 1 minus beta, right, because they are mutually exclusive to each other. One of them you reject the null, one you accept the null. In both cases, the null hypothesis is false, though. So if we, have a 20% chance of error, or type 2 error, we would have an 80% chance of power. That's kind of how that works out. I do like to comment on other ways that you can describe type 1 error here, because sometimes people get confused with my wording. Again, I like to say things a lot of different ways, just hoping that one of the ways sticks. But when we talk about type 1 error, some people are like, oh, it's the probability that we made an error, which is true, right? It's the probability that you rejected the null when you shouldn't have. But you can also describe it as it's the probability that the null hypothesis is true. Right? In both cases, you want that alpha level to be very, very small. Or you want p to be small in comparison to alpha. Right? Because if the probability that you made an error is small, that is a good thing. Right? If you have the probability that the null is true, and that probability is low, then you can reasonably assume that rejecting the null hypothesis is the right choice. So with regards to type 1 error, you can say it's the probability that you made an error in the sense that you rejected the null when you shouldn't have, or it's also the probability that the null hypothesis is true, in which case there's a very small chance that it's true, which is still related to making this error. Right, rejecting the null when the null is true. So hopefully that didn't confuse anybody, but I like to say it both ways, just in case. Okay. Things to consider. You can only commit one type of error at a time per statistical decision. So either you're making a type 1 error or you're making a type 2 error. You cannot make both. Reason being is that you're either going to be accepting the null hypothesis, which is associated with type 2 error, or you're rejecting the null hypothesis, which is associated with type 1 error. You can't both accept and reject the null, therefore you can't make a type 1 error as well as a type 2 error. Right? They are independent of one another in the sense that only one can happen at a time. The other thing is you won't know if you've committed an error. Study replication is kind of the key to understanding if an error has been made. If you can repeat someone's methods to the T and you get nearly the exact same results that they did, considering that you collected samples in the same way that they did, that would mean we have consistency. In other words, if you got the same results they did, you proved it, you had statistical significance in the same way that they did, and similar effect sizes and whatnot, that's a plus, right? That means that the actual results that both of those studies got are likely due to the intervention that was applied. If you get way different answers, that means that there might be more error than we thought existed in the previous research. So study replication is key to knowing if an error has been made, since we never know if we actually make errors or not. Non-significant findings are not always insignificant in terms of the values of the results. I've already commented on this, so I'm not going to talk about it too much more.